multiple linear regression. So if you look at multiple linear regression, it's basically when you use multiple variables to represent an observation, we call it multiple linear regression. So we have previously seen that we were only using the TV advertisement to predict the sales in a market. If we extend it to the radio, the print or the newspaper, then that becomes a multiple linear regression. Another example here would be if you have to guess someone's height, would you rather be told only their weight, weight and gender, weight, gender and income, weight, gender, income and favorite number? So in this scenario, of course, we would want as much data about a person. However, I am not sure how exactly favorite number can help us. Is it even valuable? So what we are trying to say is that they need not be strongly related. So at first you could just ignore the information so that we don't really confuse the system, or at least we expect the system to ignore such information which is not strongly correlated. So we come back to our original formulation of the advertising dataset where we have n observations and p predictors. So far we were looking into at p equal to 1. Now we are looking at p equal to 3, making it a multiple linear regression problem because you have multiple predictors. So in practice, it is unlikely that any response variable y depends solely on one predictor, say x. Rather, we expect that it is a function of multiple predictors, which we can say as f x1, x2, x3. We said p predictor, so xp, right? So we can say that if we have n observations, that is like we have x1, y1 to xn, yn, right? So we have n such observations. Right, and now so far I have been writing small x's and now all of a sudden I'm writing a capital X. That's because just to denote that each of that x, which is the, let's say an xj, sorry, an xj is nothing but we have p such values. So we are talking about x1 to xp. Maybe I can write it, yeah. Now we are going to learn, or let's say there is let's put it as j just to be aligning with our rest of the notation, right? And we are basically learning a function in a multilinear form where I am saying it's a function from x1 to xj plus epsilon, which is the error, which may be written as there is this bias or the intercept, then there is a coefficient for every feature. So naturally we are talking about the data that is originating from f of x1. So we are learning f hat for predicting y hat, where we are using values from x1 to xj, where we can say that there is a beta 0, beta 1, x1 up to beta j, xj. So again, to fit this model, we have to compute or to minimize a loss, where we will again choose the MSE or the RMSE. So please remember that we are talking about n labels because we have n observations, and each observation in itself has j predictors, and we have the bias here. Sorry, we have the coefficients here, beta 0 to beta j. So this is the matrix formulation we are talking about. So it's a simple algebraic form here. The matrix Y, which is nothing but all the n labels. It's y1 to yn. Then we have the matrix X. So Y, even though technically it's a matrix, we should say it's a vector because it's a one-dimensional matrix. So there are n observations and each y is a scalar. So for every observation there is exactly a scalar or a real number or basically a scalar value, and there are n such values, which is the outcome. Now the x in this case is not a scalar, the individual x is not a scalar, it's a vector. So my observation 1 itself have j such features and I have n such observations. So naturally there is n cross j total. So there is a matrix of size n cross j where each row represents an individual observation and there are j features for that observation. And since there are j features for the observations, we are having to learn j plus 1 weights, and this is another vector. If this is the case, we are learning a simple linear algebraic function here, which is formulation here, which is y equal to x beta plus epsilon, and then we can represent our mean squared error in this form. Now if we minimize it using the vector calculus, we can see that the vector for all the betas can be represented as x transpose x inverse x transpose y, which leads to the R min of beta or the MSE of beta. Now so far we have assumed that all the variables are quantitative, but in practice often some predictors are qualitative. For example, while we assumed everything to be quantitative, some of them can be qualitative. So let us see here. So if you look here, so if you talk about, say, there is something called as a credit data set. It contains information about balance, age, cards, education, income limit, rating, etc. for a number of potential customers. So here you may see that if the predictor takes only two values, then we create an indicator or dummy variable that takes on two possible numerical values. So if we are talking about gender here, right, it's not exactly quantitative. We are talking about a feature which has only two possible values, right? And for the gender, we simply convert them into numerical values in a manner that a particular observation has that value as 1 if that particular observation or that particular person is female, and the same is 0 if the person is male. Now here it doesn't matter if it was the other way around. If 1 implied male and 0 implied female, it didn't matter. But in quantitative ones, it might matter, right? We are talking about ordinals. If we are talking about ordinals, then it matters. So we then use this variable as a predictor in the regression after converting that into a numerical. In this case, it's just 0, right? 0 or 1, two values. So when we use this variable as a predictor in the regression, right? So if we are talking about gender, and let's assume that that gender has a coefficient beta 1. So basically, since if someone is male, then their xi will be 0. So naturally beta 1, irrespective of the value, will be 0. So we are talking about beta 0 plus epsilon I if the ith person is male, but beta 0 plus beta 1 plus epsilon I if the ith person is female, because xi can either be 1 or 0, and beta 0 was our intercept. It didn't have an x value. Epsilon also is independent. We are not talking about the rest of the betas. We are just talking about beta 1 at this moment. Now, what is the interpretation of beta 0 and beta 1? So, beta 0 is the average credit card balance amongst males, whereas beta 0 plus beta 1 is the average credit card amongst females. And beta 1 is the average difference in credit card balance between females and male. So calculate beta 0 and beta 1 for the credit card from the credit data based on this, which we will come back to later. Now let's take a little bit more complex scenario. So when we talk about qualitative predictor, like gender, we talked about 2 possible values for it. But what if there are more than 2 values? Say ethnicity. So here, a single dummy variable cannot represent all possible values. We have to create dummy variables as follows. So let us say there are 3 possible ethnicities we are considering, which is Asian, Caucasian, and I don't know, maybe European, right? So now if I have 3 such values, then I am creating a separate variable for those values. So in this case, we can say xi, the first one is 1, is xi1 is indicative of whether someone is Asian or not. xi2 is indicative of someone is Caucasian or not. And we may say that xi3 is indicative of whether someone is European or not, or Native American or not, right? So if the ith person is Native American, 0 if ith person is not Native American. So now we then use these variables as predictors, and now the regression equation becomes beta 0, beta 1 xi1, beta 2 xi2. So we are having a separate coefficient for each of it. So naturally, if someone is Asian, xi1 will be 1 and others will be 0. So we are talking about beta 0, beta 1 epsilon I. If someone is Caucasian, then beta 1 and beta 3 might not be there, but we are talking about beta 0, beta 2. Yeah. If the ith person is African American, so what they have done is that they have assumed that there is no need for a coefficient for the third scenario. In the example I have shown, even for all of the 3 ones, I have taken, I have assumed that, give me a minute. Yeah, I have assumed that there is an xi3. Naturally, there is a beta 1, beta 2. I was assuming there is a beta 3 here. So what the designers suggest here, or the slides suggest here, is that we can assume the third scenario to be like having no coefficient at all, because it's probably more optimal or more efficient. Because when we doesn't have a 1 or 2, we can say that it is beta 1 or beta 2. We can say that that person belongs to the third ethnicity, which is the African American ethnicity. So now again, coming back to our question, so far we have been assuming that whether what we model is actually forming a line, or it's actually a linear model, right, where the coefficients, all of them are linear. So if we assume a linear model, then the average effect on sales of a 1 unit increase in TV is always beta 1 regardless of the amount spent on radio. But synergy effect or interaction effect states that when an increase on the radio budget affects the effectiveness of the TV spending on sales, which means that can be interaction between the variables, which we are not capturing here. So in such scenarios, we may have such formulations where we are finding a coefficient beta 3, or we have to learn a coefficient beta 3 which captures the interaction between these two. And in some cases, we would like to use polynomial or other terms based on the input data. So we may use this, right, where we are using polynomial representation for the variables. The question is that are they still linear regression? Whether it is single or multiple is different, but are they still linear regression? So here it's very simple to understand that as long as the coefficients are linear, the equation is still a linear regression problem. That's as simple as that. So what if you have a lot of predictors, a lot of features, right? So that's why we talked about only finding relevant features. Don't use a lot of features if it's not useful, right? But let's assume you end up in a problem where you have a lot of features and all of those are relevant. Then would that really create some problem for us? Of course, it creates sparsity, which means that can lead to overfitting. It can definitely increase the computational cost. And we can think of more complex models as well. Sometimes these are required. So the simplest nonlinear model we can consider for a response y and a predictor x is a polynomial model of degree m. So just as in this case of linear regression with cross terms, polynomial regression is a special case of linear regression where we treat each as separate predictor. Thus we can write so we are treating each x power m as a separate predictor, and we write it in this form. So here again, minimizing the MSA using vector calculus yields beta hat giving MSA of beta, which can be written in this linear algebraic form. So that's most of regression for our GATE syllabus or related to GATE syllabus, and thanks a lot for watching this week's lecture. So in this week we will now cover what is remaining from the regression literature, which is the ridge regression. The only thing is that before that we might have a little bit look into overfitting and maybe some bias and variance. Some of these concepts will be covered before we get into ridge regression. Thank you.